Alright, gang, here we go. So this is Physics, Unit 4, Part 1. We're talking about circular motion. Alright? So, what I want you to do is take a second, pause the video, and look at these four things. Pick your favorite one and try to answer these three questions that are about it. Alright? Um, yeah, go ahead and do that. Alright, so I like this one the best. So let's think about this one real quick. So if you've got the Earth, right? We got the Earth right here, and then we've got the Moon above the Earth, right? And it travels in some orbit like this around the Earth, right? And so you know that objects, based on one of Newton's laws, is that objects tend to stay in motion once they're in motion, right? So really, we think the moon, like, its velocity is pointed, like, at any given moment, its velocity is pointed somewhere like this, right? So its velocity is pointed straight out. However, we know the moon doesn't just fly away from the Earth at, however fast it's going. It keeps following the Earth, right? It keeps on this path, following the motion of the Earth around, this orbital path here. And so we have to ask ourselves, well, what is causing this circular motion? The object, the velocity vector is a straight line going straight out. What's making it come back and keep turning? Well, the answer is that there's a force acting on it. And for those quick kids there, you should know that this force that's keeping it there is the force of gravity, and that's pulling it towards the center of the Earth, wherever that might be here on my Earth, right? The force of gravity is pulling it back down. So as the moon is going this way and it wants to keep traveling this way, once it's over here, right, the force of the velocity vector is going to have it shoot out that way, but the force of gravity is still going to be pointed towards the middle. And then once it's over here, it's going to be somewhere like this, and the force of gravity is going to be pulling it like that, so on and so forth. And you can imagine that as you continue to draw the position of the moon as it travels around the Earth, that it continues to do this thing. The velocity vector is pointed tangent to the path of the circle, and then the force vector is pushing towards the middle. Okay, now as we look at these other guys here, you'll notice that the same thing kind of happens, like a car traveling around a circular ramp, or so it's going in circles, right? You could imagine a race car or something like that, a NASCAR. It's going around and around and around, and it's the vector of the velocity is always going to want to go straight out from whatever path it's taking, but in all cases, there's some sort of force that's dragging it back towards the middle. Okay, imagine like taking a ball and swinging it around in the air, like so on. So the tension of the string is pulling the ball back towards the center of the circle. And so that's really what we're focusing on today: is what's causing that circular motion. And the idea is that we have this new force called the centripetal force, and we'll get to that. But first, we need to cover a couple of vocabulary words here. First is tangential speed, and so this is the speed that's in the direction tangent to the circle. Now remember, the tangent is is defined, like we've talked about this before, but so the tangent line is a line that hits the circle at just one point, and so we say that's tangent. So that's the speed in that direction. All right, that's tangent to the circle, and this should be a subscript t. So let's rewrite this here, v sub t. And so if you have uniform circular motion, so that means it's traveling at constant speed in a perfect circle, your tangential speed has a constant value, and the direction is changing. Okay, so here you've got you've got this guy here at point A, and he's moving this way, and then his final velocity is this way. Notice that the magnitude of these lines is the same, but they're pointed in different directions. All right. So the other idea to think about is if you're imagine that you're on a carousel here, right? And it's like one of those carousel with the horses that go up and down as they go around, right? I really suck at drawing, so I'm kind of avoiding, but it's just what it's gonna have to be. And so say you're a kid that's on a horse over here, and then your center of your carousel is right here, and then you're on another kid that's on a same type of horse, but towards the center. Now you know that this carousel is going to be traveling, so that this point here is going to travel all the way around the circle in an equal amount of time. So everything that's around this line here it's going to make one trip around the circle in the same same amount of time. So you could say it takes like 30 seconds to get around the circle. Well, the horse at the end has to travel a much farther distance because it has a much larger circumference area to cover, right? It has to follow this whole edge of the circle as it goes around, whereas this guy in the middle has a much shorter distance to travel. And so he's got a lot slower tangential speed. So there's lots of applications to this, like, this is like one of the main reasons that, drivers, race drivers and runners and stuff like that all, want to try to get the inside edge as they go around a corner, because if you're on the inside, you don't have to go as fast to cover as much distance. All right, and so this idea of tangential speed is an important idea. Now, think about it this way: like we know that velocity is always equal to the distance over the time, the distance you travel over the change in time. Specifically, though, the tangential speed, the distance that we're traveling, is the circumference of our circle, and the circumference of our circle is equal to 2 pi r. Right? So this is an important concept. The tangential speed is going to be equal to 2 pi r over t. All right, centripetal acceleration. So we know that our velocity is changing, right? And whether these magnitudes are the same or different doesn't really matter. What we do know is that the direction is definitely changing. Right here, we're pointed off this direction. Over here, we're pointed down farther. And we know that anytime we have a change in velocity, we always have to have some sort of acceleration. This acceleration in a circular motion is called the centripetal acceleration. All right. And so this is the acceleration that describes the motion of our object as it travels in a circle. All right. So the idea is that we're going to have two different accelerations here. One that's in the same direction as our tangential velocity, and one that's center-seeking. The centripetal acceleration is the one that's center-seeking, and we'll talk about tangential acceleration here in a second. Okay. So as your ball goes around, because you can imagine like the difference between these two vectors here is the vector of the acceleration is going to be pointed down into the center, right? And you can imagine that if you did another one that was like, like this, I'm not going to, this is what happens when I try to draw things on the fly. And so the distance between those two vectors is, again, you're going to be pointed down and towards the center. And then if we do it again, so here we go. So you got your circle, and then so you get another time. You get another time that starts right here, and so this is going to be pointed down like this, and then the difference between those two is it's going to be pointing down and towards the center. And so as you go, you get this acceleration that's pointing down and towards the center of your circle, and so we call that the centripetal acceleration. All right. So this is your formula to find the centripetal acceleration. Okay, and really what happens is that this question here is very important. So as the magnitude of your acceleration, what's its relationship to the radius? So you can imagine that if you have a ball and you're swinging it around, the bigger the radius is of the circle, the slower the acceleration, that centripetal acceleration, needs to be, because it's changing its direction a lot slower. It's making a very big circle, so the amount of change that it needs to make is very slow. Whereas if you bring that and start swinging and you make that radius smaller and you swing it tighter, then that acceleration needs to be much greater, because it's changing its direction much quicker. All right. And then the last one here, this next idea of acceleration, is the tangential acceleration. And this is the acceleration that's directed tangent to the circle. So remember, our centripetal acceleration was pointed inwards. Our tangential acceleration is the one that's pointing outwards. So if we have, our circle here, and then we've got, you can imagine that you might have some sort of object that's, got some velocity, some initial velocity that's there, and then as it's going around the corner, it slows way down. I hate that it does that. All right, and then so it slows way down. Oh my gosh. And so now the final velocity is going to be much smaller. And so the change in the magnitude of the speed is defined as the tangential acceleration. All right. So this change is in this tangential speed is going to be called tangential acceleration. All right, and so on the notes packet, I set this so you can type this link in here right there, and so you can watch this video. It kind of does a really good job explaining what's going on with centripetal versus tangential accelerations. All right. Now, finally, we know that because of Newton's second law, anytime we have an acceleration, that's always caused by a force. We call this force that's causing a circular motion the centripetal force, and Fc is the symbol for it, Fc, centripetal force. And so here, this blue box is them deriving it. You don't really need to understand this too much, all right? But you should be able to recognize that we have, F equals ma, and then a is, this is our acceleration, tangential or centripetal acceleration, and then we can just kind of plug in these values here in order to get our centripetal force and just kind of substitute them in. Anyway, and so this is our equation for centripetal force, mvt squared over r. So, vt is our tangential speed. Okay, and notice once again that our centripetal force is pointed in the same direction as our acceleration. All right. Now, our centripetal force is what allows us to maintain the motion in a circle. So if we got rid of, the easy way to think about this, in my opinion, is that if we think about getting rid of that centripetal force, so if you're swinging this ball in a circle that goes around and around and around, and then you cut the string, that's essentially getting rid of that centripetal force. Without that centripetal force, then your ball isn't going to be center seeking anymore, and so now it's going to be flinging outward. Okay, and you're going to travel in a straight line tangential to whatever point you were at on your circle. All right, and so really we can cause the centripetal force by lots of different things. In the planet's case, the moon orbiting the Earth, it was gravity. Okay, like this ball and string, like here, this this was caused by the tension in the string, right? And then a car that's turning, in a circle around a roundabout, well, the reason it's center-seeking, that centripetal force, is caused by the friction of the tires on the car. Now, think about that for a second. Like if you're out on icy roads and you go to try to make a sharp turn, and you hit an ice patch, well, what direction do you go? You might be turning your wheel to the left or the right, but if there's no friction of the tires on the road, then your car is going to keep going in whatever straight line you were headed. All right, so your car going to the left or the right is really just caused by friction. All right, and you're always going to be headed in a straight line once that force is removed. All right. Now, think about this for a second. There's a misconception that you'll hear a lot of people throw out. Okay, so just bear with me for a second. So imagine yourself, you're the passenger in a car that's turning to the left. So you're in the passenger car seat, you turn to the left real quick, and you don't have a seatbelt on, so you're just kind of sitting there. How do you feel during the turn? Well, to me, when I imagine it, I turn and I feel like I'm being flung to the right, right? Even though we're turning to the left, I can feel myself go, whoa, to the right, So the force that's acting on me, I feel like something's pushing me to the right. Right, that's kind of how it feels, because I feel I'm being pushed to the right. But the problem is that there's no force actually doing that. That's pushing you away from the center. Remember, we talked about centripetal force. That's the force that's being pulled towards the center of your circle. But there's no such thing as like the opposite force. Now, there is. You'll hear lots of people call, well, that's centrifugal force. This pushing you away from the center. That's not a real force. It's a false force. It's a force that you feel that doesn't really exist. Now, what's really causing about it is that you, as a moving thing with mass, you have inertia. Remember, your inertia is causing you to move in a straight line or a given path until something stops you, right? So you're going and you have inertia, and you're going tangential. So as the car starts turning to the left, you're going to want to continue. Your inertia is going to want to continue pushing you tangent to the circle in a straight line. But what happens is as you go forward, the car has the friction of the centripetal force pushing it to the left, and so you're really just hitting the door of the car, and the car is pushing you back around, and so you feel the force of the car on you, pushing you to the left as you go around the circle. It's kind of bizarre and totally different. So if you ever hear anybody talk about centrifugal force, that's not a real thing. You can kind of show them as, oh, that's a false force. You're full of it. It's only centripetal force. You just think you're feeling centrifugal force. All right. Oh, here we go. What are you doing? All right, so let's try a practice problem. Notice that I got the answers here at the bottom. But this is a pretty easy plug and chug kind of experience here. So you've got a 35 kilogram child, and he's on a circular path with a radius of 2.5 meters, and you're spinning around a playground merry-go-round. You make one complete revolution every 2.25 seconds. What is the speed or tangential velocity? So we know tangential velocity is equal to, well, we know from earlier when we talked about it that it's equal to 2 pi r over t, right? And so 2 times pi times your radius of the circle, which is 2.5, all right, over the time, which is 2.25. All right, so we can plug all that into our calculator. 2 times pi times 2.5, and then we'll divide that by 2.25. And we get 6.98. Remember our sig figs, 3 sig figs, so 6.98, and velocity is meters per second. So 6.98 meters per second. All right, now we want a centripetal acceleration. Well, centripetal acceleration was equal to, well, let's just double check here. I'd hate to do it wrong. Centripetal acceleration is t squared over r. I knew it. Okay, vt squared over r. All right, so we go vt squared over r. All right, so our VT squared, we just found our VT, so that's easy. So that's just the 6.98 meters per second, and we're going to square that sucker, divided by the radius, which is the 2.5 meters. All right, and so that's that. So we take our 6.98 squared, divided by our 2.5, and I got 19.4955. So the 3 sig figs, that rounds to 19.5. And because it's acceleration, it's going to be in meters per second squared. And then lastly, it asked for centripetal force. So that'd be Fc. Well, centripetal force is our formula right here, right? mvt squared over r. So mass times velocity squared over r. So that's our mass times velocity squared over r. All right, so the mass of the child is 35 kilograms, 0 kilograms, and the velocity is that 6.98 meters per second, and we're squaring that, divided by our radius, which is still the 2.5 meters. So that means our centripetal force is equal to, so we'll take our 35 times 6.98 squared divided by 2.5. We got 3 sig figs, 682, and the units for force is 682. Why did I write 68? 682 newtons. All right. So anyway, so that's that. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.